thank you. Churchill asked me to come about and speak, and I had imagined sort of a nice little chat with maybe 20, 30 people here, and I could sit down, relax, and we could have a little bit of a chat. This doesn't seem feasible. That kind of stuff doesn't scale. So I put my ideas on some slides, and so I'm giving you a fairly straight lecture, and then at the end we'll have time for a lot of questions and answers to sort of imitate what this was supposed to be in the first place. To help me give this talk, I have a simple question. There are two parts to this talk. Some that is sort of history and background stuff, and then there's a little bit of code for people who like code. So to figure out what the balance is, I would like to know who knows something about software. And it's a very simple question. I mean, do you think you can read about a page of code in any language at all? If you can do that, just raise your hand. Wow, I will show the code. Good. Okay, so, and let's see. This is about code. And so I chose a Lego wind turbine, because wind turbines are C++ usually, and so is Lego. The Lego is from 100 kilometers from my hometown. Vesta, as we're making those things, were headquarters in my hometown, so it's a wee bit of nationalism here. The outline of what I'm going to do is to try and explain why this is interesting, and then give some background of what C++ is, where it came from. I'll show a few places, then go into how it evolved, what kind of ideas seems to have driven the evolution of C++. Then I'm going to show you some code. We'll see how time goes there. And then I'm going to say a word or two about how I think you should write good code, and then have the Q&A. And at the first approximation, C++ is everywhere. It'll be in your phones, in your televisions, in your cars, in your coffee machines, things like that. If you have fancy watches, mine isn't fancy, there will be quite often be C++ in them, so it works in tiny things. I just saw 2 days ago some project that somebody had been doing with primary school children. You got a little thing with lights on, and it could play Happy Birthday to you, and you could blow out the LEDs. This was done by, there was a microphone, and when you blew just right, a light went out. Ta-da! 2,000 bytes of memory, all done in C++. So you really don't know where it is. I don't know where it is, but it's interesting. And then, I mean, there's the internet, there's C++ out in space, and a lot of the server farms are in C++. And I really don't like language wars, so I don't say rude things about C++ applications. Because how do you think these languages and systems are implemented? You don't actually write them in themselves, you write them in C++. And I like science, of course. There's the Large Hadron Collider in CERN, another nice application. I mean, how you program something to work correctly when you are dealing with relativistic speeds. You most certainly can't synchronize those magnets from the central point. It's 27 kilometers long. So it's mind-blowing. There's a large community for C++, about 4.5 million. When you do surveys, if you go and listen to the web and see how much people talk about different languages, what you measure is noise. And one student can make far more noise than, say, 200 developers that are actually trying to deliver this kind of stuff. They're too busy to go into language wars. And again, I look at the surveys. The community seems to be growing by maybe 100,000 developers per year. And so you go and listen to the press, and you find that some language has grown by a factor of 2, and therefore is the language of the year. Maybe they grew from 25,000 to 50,000. C++ doesn't count because our percentages are low. And I've been trying to keep track of where things are. I used to joke that if this doesn't work, I have to escape to Ulaanbaatar. Won't work. Not anymore. And it's in most industries. But from my perspective, the nasty thing is you never see it. It's like what they say about housework. You only see it if it isn't done. If you notice a C++ program, there's probably something wrong. If it's driving, you're running your car, your television, or your graphics, a lot of graphics is C++, you don't want to know it. You don't want to have to know it. It's just done right. And as one way, there's many ways to see how a programming language is nice. It could be elegant, it could look like the best math, or it could be easy to translate, or it could be easy to use. C++ would lose out in a lot of those measures. But my measure has always been, what can you do with the language? The purpose of the language, in my opinion, is to build applications, to build good, useful stuff that people can do. The code is never the end product. It's what you do with the code. I mean, maybe it's a calculation of an orbit. Maybe it's a decision of when to stop an elevator on the way down. But it's the end product that matters. And so that's my measure of success, and it's been doing all right. When I was here in Cambridge, I studied distributed systems, and I'm still doing it. There's a distributed system on wheels. That these things are controlled by a network of processors that do all the interesting things. So it's still there. Let's see. I was going to tell the story about C++, and so it starts when I was in my hometown of Denmark, which is a very nice place. If you get a chance, you should visit it. It's a nice place. It's a walking place. The food is good. The weather is good in the summer. And so I was brought up roughly, if I stand like this over there, sort of about 15 minutes walk from there. And I went to the local university, or University of Aarhus, which was quite a good university, I think. I actually wanted to go and study engineering in Copenhagen, but I chickened out. 2 reasons. One, Copenhagen looked like a big bad city far away. It's a small place, Denmark. And secondly, I would have to take out loans to live for. Education is, of course, free in Denmark, but living isn't. You need bread and beer and a roof over your head. So I went to University of Aarhus. And that's sort of like my first computer, except this is a deluxe model, and it's only the table you control it with. The real computer is sort of from here over to the wall. Had 1,000 words of memory, really big computer in those days. And only one paper tape. That's a We didn't have a fancy typewriter like that, but you could flip the switches to start it with that one. It was called a regnecentral gear machine. And so I couldn't study computer science at the time because like here, you started out in math. And so I studied math for a while. My first degree is officially in math with computer science. I didn't actually know I was signing up for computer science because the Danish word for computer science at the time was datalogi, which is sort of an invented word, and if you know your Greek, you can probably figure out what it means. Well, I didn't, and I thought I had signed up for applied math. It turned out to be good that I was wrong, because like a lot of people, I found I wasn't as good as math as I thought I was. On the other hand, I hit programming and machine architectures, and I was hooked. I'm still doing it. Good stuff. So after I sort of ran out of really interesting things to do in Aarhus, and I wanted some fancier machines, I ended up in Cambridge to do a PhD. That's the old computer lab, brutalist architecture, but nicely placed down in town. And I was about to get married at the time, so I actually chose Churchill, not because it was close to the computer lab, because it wasn't in those days, but because it had the best graduate student accommodation. And it's actually important because you don't just do your work 24 hours in the lab. You actually have to sleep and have a social life and such. So I went for this. It was very nice. And our oldest daughter was born here. They told me that if they'd had a Winston Churchill look-alike competition for babies, she would have won. There was some discussion of having this, but we didn't want to give cigars to the babies. That actually was the computer I worked on for most of my PhD. This is a Cambridge cab computer designed by Maurice Wilkes and David Wheeler and Roger Needham. And that was a beautiful piece of equipment. It's still standing over. Last I checked, it was standing over in the hallway so you can see it, though you're not allowed to open it up. Inside, it's beautiful, at least if you like that kind of electrical engineering kind of stuff. But it's a beautiful piece of equipment. The way I got to that one actually was that I wanted to study distributed systems, and I wanted to study how hardware can support software by making a better machine for the software to run on, because of a lot of complexity and the horrors of software is when it has to interact with hardware. So my first idea was, let's fix the hardware. And this one has many good ideas. But anyway, I was writing simulations, and I finally got my simulation to run over on the one and only mainframe that the university had. And it soaked up a lot of time, and I was told, politely but firmly, that you will never do that again. The physicists and the chemists and such really need their computer. You can't have one PhD student soak it all up. So I had to find a machine that was so badly supported in terms of standard software that the physicists and the chemists couldn't use it. That one. It was far more beautiful, and I have been told, whether it's true or not, I don't know, that I actually used more of that machine than everybody else put together in its lifetime. It was fun. I had a good time with that. But I actually learned something. You can't soak up all the resources because there's other people there, and you must actually be reasonably economic with what you use. And things like simulations and graphics and games and whatever always uses all the compute power you've got and all the memory you've got. And this is independent of what kind of machine you have, because you always want a little bit more. The only thing that grows faster than computer performance is human expectations. It was a conclusion that sort of started here and then got firmer over the years, and I still believe it. It is the basis of a lot of my thoughts, because I get told all the time machines are so efficient these days. We don't need efficient software. We can just use it up. If you're too slow, next year the machines run faster. Well, in 2005 they stopped running faster next year. And anyway, this is fine. So after Cambridge, I went to Bell Labs. The way that happened was actually at 6 o'clock, when they still had opening times, people from the computer lab down on Corn Exchange Street ambled over to the Eagle for a pint and some gossip. And we had somebody who had left for Bell Labs, and over a pint he told me, if you need a job, why don't you give us a call? Tell us about it. And so when I got closer to the PhD, I gave them a call and said, sure, drop by. We don't have a recruiting budget because we're not recruiting, so we may not be able to pay your fare. So, yeah, bummer. I didn't have any money, but I needed a job. So I went over there, and the first thing they told me was, we don't have any jobs. I was still seriously jet-lagged at that point. And so I talked to some people, including these guys, Dennis Ritchie, Ken Thompson, and a lot of nice guys. Sandy Fraser, who was my boss at the time, studied here, so there was a connection back. And after 3 days, they changed their mind, and I worked there for the next 24 years. That was the machine we had. It's a PDP 1170, for those of you who are interested in those things. Really nice machine. The I/O devices were a bit primitive for the time, and there were switches you had to flick to start it. But this was where Unix started. And so anybody who's used Unix, which is almost all of you, directly or indirectly, and actually it's creeping into Windows and such. So a lot of that stuff came from right there. And so this was a very interesting place with lots of interesting people. That's the Murray Hill building for Bell Labs. It's still there. It doesn't have as many interesting people on the inside, but it's still there. That tower over there, and the next floors down, was where the computer science research were done. And so I was there for a while. The deal I got was a dream deal. Basically, do something useful, and after a year, tell us what you did. Here's an office, here's a computer. Hey, what's wrong with that? After you've stared at the computer on the wall for a while, you realize that's not actually easy. Most people like to be told what to do because it's so much easier. Then you just do it. Also worse, I walked around the hall and I saw the names on the walls, and I saw what they've been doing. Ken and Dennis there, Brian Kernighan, Al Aho, Bob Morris. They were doing everything. In other words, something useful was sort of off my usual scale. It's like Cambridge. This is a place that can inspire you to do better, just because you get the feeling that if I don't up my game, I guess I don't belong here. So you better up your game. And so I worked harder. So the origins of the C++ was a project at Bell Labs. I wanted to build a Unix cluster or multiprocessor system. The idea was to get a whole bunch of computers to collaborate on a task, and for that you needed to take the system apart and take the services from the operating system apart. So you have something over here, and they talk. And to do that, I needed two things. I needed close to optimal low-level programming. I needed to write process schedulers, memory managers, network drivers, device drivers, all this kind of grubby stuff close to the machine. This was fine. Lots of languages could do that. And the other thing I needed to do was define this and that and how they talk. And there's lots of languages that could do that. There were high-level languages that had facilities for defining abstractions like things in a certain location and communication protocols and channels, all kinds of good things. To my great surprise, no language could do both. So I either had to back out of my project or get a language that could do both. So I took the ideas from Simula, which is a high-level language, the language that started object-oriented programming, designed in Oslo a few years before. And I knew it because the main designer of that used to visit Aarhus, and my office was just at the bottom of the stairs to the visitor's office, so I was the student delegated to round up some students to talk with and some beers to go with it. And C, the language I used, actually started in the computer lab. There was CPL, then BCPL, then B, then C. So the origins of that language, which is also what runs Linux these days and has run a lot of things. A lot of you have heard about it. C had its origins here. So it sort of adds up by luck, but it adds up. And one of the things I was rather keen on was to keep the facilities general and flexible. So I didn't want to build a distributed computing language. I wanted to build a general purpose language that was good for building distributed systems and other things, because I had realized that you change your mind after a time, your tasks change, your friends want to do something that's like what you're doing but different. So if I just build my solution into the language, it's not going to be flexible enough. Furthermore, I had a fairly keen understanding of my own limitations, so if I did something, I could only do what I could think of, I would fail, because a group like this, or any other large group of clever people, can think of much more things than I can think of. And so I built C with classes first, C plus classes, right? And no, I never got to build the system because C with classes and later C++ got popular, so my friends and colleagues started building things with it, and then I had to help them, and I never got to. Became a tool builder. That's sort of the 1985 vintage Bjarne. So a way of looking at C++ from a little bit more fundamental thing is there's two lines of development of languages. There's stay close to the hardware, manipulate hardware, make sure that every byte and every cycle counts. That starts with assembler. That is David Wheeler, my advisor. And he built some of the first computers, some of the first compilers. The EDSAC machine done here was, to a large extent, his work, and he helped write the first book on how to program. From there, we got BCPL also here. Then it somehow got over to the States via Martin Richards going to MIT and needing a language. And Dennis Ritchie picked up some of those ideas and built it to the C language at Bell Labs. But basically, here is where you want to be close to the hardware, you want to use every cycle and every byte. On the other hand, close to the hardware is not a very pleasant place to be. I mean, it's hardware, it's not really built for humans, it's built for to run fast and to It changes, and as you get improvements and such. Not very pleasant thing. No abstractions to help you think about your problems. So up here in 56, Bacchus, that's Bacchus, built Fortran with a team at IBM. And the idea was that you wanted to build a language that was suitable for humans, that is, focus on the task to be done rather than the machine. And the humans they thought about was engineers and scientists, and they built something that could do formulas and then translate them, hence Fortran, formula translation. And as soon as the engineers and scientists got their own language that everybody wanted one too, COBOL for the business people. And after a couple of years, there were about 200 languages. And I think the major improvement here, the major breakthrough, was this idea of lifting the programming from the machine up to the application area. And we've been working to make that better ever since. Simula was an attempt to unify all of this. So instead of having Fortran has built-in abstractions for doing sort of math-like things, you can do linear algebra rather well. And COBOL is built with abstractions appropriate for business people, so they can do file transfers and copies of records and dealing with Mac tapes and such stuff. And things looked very different in these languages. So Fortran, X becomes Y plus Z. Fine. Plus is a plus, equals is equals. That was considered unsuitable for business applications, so it becomes Y, add Y to Z yielding X. All of this spelled out with letters, capital letters in the old days. So these were different. So we thought, instead of building these abstractions in, why don't we give people, programmers, the ability to build their own? If you want linear algebra, build some matrix classes and operations of matrices, fine. If you want to have records and copies of records and things like that, build that. And so in Simula, they built a set of user-defined types called classes at the time because, well, these guys were trained as mathematicians and didn't know about types, but they knew about classes and sets and things like that. So if you have seen any language that uses the word class to mean type, you can thank him. And so I took those two ideas and built C++. The idea that I can do fairly arbitrary abstractions, you build your own. If the type isn't there, build your own. But make it affordable so it can run close to the hardware and really fast. And from that, lots of interesting things goes on. I'm still working on it. We are just finishing C++ 20. Most of that is shipping already, a year in ahead of time, but we're getting an improved language. This has something to do with the fact that when I did this, to begin with, I knew very well that I couldn't do everything I wanted. So I had to build something with the idea of evolving it. And I've been doing that ever since. So C++ in 2 lines. There's a direct map to hardware, and there's zero overhead abstractions. That is, you can build your own types and uses of your own type. Zero abstraction means it's cheap, preferably free. That is, you can build things that are as good as in a high-level way. You can use them in a high-level way as well as you could have gotten the performance by using the grubby low-level stuff. Let me say what that means a little bit. So a direct map to hardware means that the primitive operations map to machine instructions. Add 2 integers, you get an integer add. Add 2 floating point numbers, you get a floating point add. You don't get some interpretive thing that says, there's 2 thingies here. What kind of thingies are they? How can we do the right thing for these thingies? Whatever, types, classes, built-in types, whatever. That's not what it does. The compiler figures out you've got 2 ints. It knows how big those ints are, and it uses the optimal instruction. And next, memory is just a sequence of objects that you can address with addresses. This is just what a machine is. There's other things in the machine, but basically that's what it is. And you can compose objects. If you want an array, a vector, you just stick a bunch of values with the same type next to each other. If you want a more composite object, you can have handles and values and of different types, and you build a structure or a class out of that. And this is really, really simple. There's nothing high level here. There's no mathematical abstractions. This is just what a machine is. A machine is many other things. There's no registers on this on this slide. There's no caches. So that can be a problem sometimes. But basically, this is a treaty between the compiler implementers and the machine architects. And this is the basic idea that came out of Dennis Ritchie's work, and I borrowed. This is the way you can squeeze a lot of performance out of a machine. You have your high-level abstractions that map to this view of the world, and then you have the optimizers and the hardware architects working below that. And I've been using the word abstraction a fair bit. Basically, when we are talking about things in the world, we don't actually look at all of the things all of the time. We abstract to something that we need to manipulate with, that we need to think about to simplify our thinking. So this is sort of a car, right? Except that it isn't a car. It has been simplified, it's been made transparent so we can see the innards. The bits and pieces that are in here are hooked together, but they're sort of not quite with all the details that are there. They are an abstraction of what's in the car. And so for software and hardware, we make things out of parts. You can see the parts there, and the parts tend to be made out of parts. But when we're using a part, we don't think of the parts it's made out of. We don't want to talk about driving cars and having to think very much about the suspension. When we're driving a car, we just think about the car. When we think about something going wrong, we take sort of one layer off and say, is there something wrong with the suspension? It's bumping. And if it really is a suspension, we start looking, well, there's a spring there, and there's some hydraulic, and so, yeah. Anyway, so we can go down basically from the car and through endless layers of abstraction that we can think about, so we actually hit the atoms and things like that, which the physicists tell me are also abstractions. So it's abstractions all the way down. Or as some people say, this is turtles all the way down. So basically, some parts are custom built, some parts are custom fitted, some parts are used in lots and lots of places because we didn't actually need to optimize that particular part very carefully, so we could use it for all models of cars, and some things don't actually even have to be in cars. If you have an electromotor, maybe it's used for lifting car windows. Maybe it's used to open gates or something. It's just an electric motor, right? It's a part that can be used elsewhere. So one way of thinking about software, and one way that I think about it a lot, is you have to pick the right level of abstraction, you have to pick the right parts, and then you have to figure out, can I borrow somebody else's parts? That's even better. Then I don't have to make them. I don't have to debug them, find the errors. And so this is a picture of a car. But if you think about it, it's also a picture of the software that you depend on, because, well, not just because there's software in the car, but also because that's a sort of a metaphor for how you put your software together out of parts. So what does it look like in code? Steve Hawkins said that if you show one equation in a book, you lose half of the audience. I am going to risk to show you some code. which has the same kind of property if you don't explain it much. But basically, you saw the picture of the memory. There's a set of objects, and you have a pointer to it. There is a pointer called lm that points to some memory. This integer says how many elements there are that's being pointed to. That's that bit there. What I want is to lift the level of abstraction to somewhere where I can say there's a vector, and it has n elements. And if I want some more elements, I can extend it. In other words, I'm away from this really low-level thing, and that's what I do here. I define a type called vector. Thank you, Christian Nygaard. And it's a template, which means that the elements are of a type I don't have to specify here. I specify it when I use the vector. And I have two operations I pointed out here: how you make a vector and how you get rid of a vector. That is, when you build a vector, you have to have memory for holding its elements. And when you're finished with a vector, that memory has to be given back to the operating system. So that one here, you give it a list of elements, and it makes up a vector filled with elements down there. And when we're finished, we give that memory back. So here's an example: vector of doubles, constants. So here it's initialized to a bunch of well-known constants, hopefully well-known to somebody. And we can take a vector of strings, of designers, of well-known programming languages, BCPL, C, similar. And so what we have here is sort of this idea: at the bottom it's all code, and you start with the lowest level of code, which is really close to the machine, and then you have to build operations like initializing the vector and cleaning up the vector. And once you've got a vector, we can start building the rest we want. We want subscripting, we want copying and things like that. But once we're off the ground with having made a vector, we can do fine. And it's sort of flexible. I don't care what the vector is a vector of, because the notion of a sequence of elements you can subscript is independent of what the type of the elements are. There's a lot of abstraction here, and we can do the initialization. So, going away from the code. So what I really think about when I work is quite often what applications are being built, the code that's being used to it. There's a lot of developers there. Developers, they can be like craftsmen, or they can be like people on an assembly line, they can be like artists, but there's certainly people there that matter. And once you're thinking about programming languages and programming techniques and such, you have to remember it's people, and you have to do things that sort of suit. That happens to be my friend Alex Stefanov, who invented, among other things, vectors like that. And a lot of good algorithm stuff. There's a lot of scientists and places. One of the things that keeps me going is that I can go and talk applications with interesting people in interesting places. That is Mauna Kea in Hawaii. Those are the telescopes. You can actually, in the summer, take a nice swim in the morning, go up there, have a snowball fight, talk to some astronomers, see some interesting, very large gadgets, and then go back for a good fish dinner on the shore. And the cool places, cool people, that matters. And, well, maybe you can go and talk to people who build telephones or communication systems, base stations for telephones, graphics that goes on them. One of the things I really, really like about computer science is that it doesn't actually matter what it is. If you're interested in it, somebody in it, be it automobile manufacturer or astronomy, somebody doing it is using software. And so you have a perfect excuse for going and talking to them and learning about these things. I think I'm in the best field that there is for that reason. I'm sure you can all make an argument like that for your own field, but this is my argument for my field. And what matters, again, it's people. The programming language is a tool, not an end goal. And we want great systems, not programming languages. Most of the time we don't see programming languages. Yes, there's 4.5 million people in the world that writes C++ code. There's probably about 10, 12 million people in the world that writes in any language. You can, depending on what you mean by write, and whether you mean full-time or part-time and such, you get numbers in 10, 20 million, something like that. And the other 6 billion of us are interested in what's being done, not how it's being done. Most people don't want to know how sausages are made. I happen to be interested in how to make these particular sausages, but let's not forget what it is. And software developers want great tools. Now, once back in Aarhus, I still had to have some money to live while I got my master's. So I got into building little systems for local businesses that ran on computers built into a desk. They were doing things like a straight ledger, writing bills, calculating mortgages and things like that. And once I was sitting in a house out in the suburbs while mom and dad in a mom and pop operation were doing the final checkout of my handiwork to approval test. They were sort of typing. It's nothing fancy, and they were typing and seeing if the right things were coming out on the printer, and they typed the right things like that. And I ended up sitting in the sofa in the next room with 2 really cute little children, chatting with them. And it dawned on me that if I screw up, I'm hurting these kids. Better not screw up. And so that's part of where I come from. I'm very keen on reliability. I'm very keen on certain forms of correctness. It's not just whether your brakes actually engage when you hit the pedal, the brake pedal, but also very concrete. There's people here. So in software, lots of things matters. It's far too much to talk about in one talk. Stability, evolution to catch up with a tool change. How do you teach this stuff? One of the things I'm horrified by is quite often how badly C++ is taught. So I after many years, became a teacher and wrote some textbooks trying to help with that. Got an email this morning from Shanghai. They estimate that 20 million children will have been taught C++ in the next 5 years. Better not screw up. There's a responsibility here. It's not just fun and game and going to cool places and seeing cool people. They have to get things done right. One thing that distinguishes industrial work from academic work is that you have to build a complete system. So it is not enough to be the best in the world of one or two things. There's this old saying that no chain is stronger than its weakest link. In the same way, you are not programming in a language, you're programming in a tool chain where you have to do all kinds of things. So either everything can be good enough, not necessarily the world's best, but everything has to be good enough for what you're trying to do, or somebody will use some different tool. So I'm trying not to over-optimize the language for any one particular thing. That means you have to listen to a lot of people, and you have to keep solving real problems for real people under real world constraints. That's very different from writing a nice paper. You may recognize the bike shed there. It was actually there because we have the notion from Parkinson that people having bike shed discussions. That is, people will have discussions about everything that isn't really on this slide. because it's easier to talk about the bike shed than the main issue. And C++'s role in the world is sort of trying to write elegant and efficient code. And that's done by defining lightweight abstractions, in other words, building types and uses of types that you can do something useful with and you can afford to do it with. It's not enough to have the most elegant code. You have to have the most elegant code that people can afford to use for their practical applications. That's where the zero overhead abstraction comes in. And C++ tend to be rather good if you're resource constrained. So if you're running a Google or a Facebook data center, you have a few 100,000 processors and terabytes of memory, and they always run out of compute power and memory. So they have to build a new one. The new one costs $60 million, but their price is going up. Okay, and it costs as much as a small city to run. So you really want to be efficient in that. They're resource constrained, memory, electricity, processing power. And then the watches. I really should get myself a fancy watch so when I point here, it's meaningful. But, I mean, these things are supercomputers, but they still run out of battery, and they still don't have enough memory for a lot of people. But the interesting things are actually the ones that are smaller. So resource-constrained applications and software infrastructure. A lot of stuff is being done in C++ for building infrastructure for other things. C++ is not the most common programming language in the world. It wasn't meant to. It was meant to work in this level above the hardware, to use hardware well and provide good abstractions. And so you build really nice abstractions like TensorFlow is the abstraction that you use for AI ML, artificial intelligence, machine learning, which is usually done in Python. And so programmers tend not to use the C++ code. They use the Python code that uses the C++ code. So sometimes your users are not actually people, they are other programming languages. And so one thing I have to remember, no language is perfect for everything and for everybody. If somebody comes and says they have a perfect language for everything and everybody, there are basically two choices. Could be a salesman, could be a fool, and probably both. So sometimes we have problems. There's a famous book by my friend Alejo about how to build compilers. It shows the dragon of complexity being killed by the knight armed with the weapons of computer science. Sometimes the dragon wins. We have to remember that. It's also encouraging because that means there's more work to be done. There's more interesting problems to solve. And this is going to go on for a while. So for C++'s evolution, we have it's going on with new releases coming now every 3 years. And basically, I've been borrowing from a couple of philosophers here, dream no little dreams. I want something that's type and resource safe. Some of you know what that means. I want it to be as faster than anything else. Better at using resources. That's easy to understand. It should use modern hardware well. Hardware is changing dramatically now. Because since they don't run any faster for a single processor, to run any faster, it gets so hot that it melts. So you don't do that. Instead, you're using your transistors on the chip in other ways. You build more processors, more clever memory and such. And so we have to actually evolve the language to keep up with that hardware. And we want the compilation to help give us more correct programs. And then the best is the enemy of the good. If you deal with a bunch of people trying to get some work done, you'll find that just about everybody is trying to polish their little part of the system to be perfect. And that means they'll never get finished, and it's not there for other people to use. We have a standards committee for C++ that currently you have 230 people turn up at meetings. That's significantly more than there's in this room, and you have to get them to agree. This is hard, so the best is the enemy of the good. Sometimes you just have to ship the next one and then fix it. This has been the case for C++ forever. And so the world has changed, and I think C++ has been part of it. So when I started, this was an advanced modern telephone. That's where you get your communication and your power from. And surprisingly, it has to be attached to the wall to do anything. And basically, the only thing is you can push some buttons and then you can talk to somebody in the other end, except there's advanced features like you can leave a message. That's it. That's 1979 or thereabouts. This is a modern phone. It's not quite to scale. This one has been scaled up so that you can see it. You know how big a telephone is these days. What do they call them now? Devices? That's correct, because this is a supercomputer with a screen that can also act as a telephone. And so the world has just changed dramatically. And so I'm arguing that programming languages should change also. The only problem is there's a few 100 billion lines of code out there. So you must improve things, but you can't break all that, your other stuff, because the other stuff runs our world. I think I've been pointing out that if our computers stopped working, suddenly we would starve. The transport systems bringing us food will not work. The tractors the farmers use will not run. The pig farms relies on computers. I talked to some people running pig farms, how you measure the swill out for the pigs, how the pigs stand on a scale while it's being fed, so you can see how much of the swill it actually eats, takes a temperature to see whether it's well and happy. Whether it's the right pig in the right store, all of that kind of stuff is computerized. If this stuff stops working, we're in deep trouble. Let's see. We are how long in?
Well, we've got 25 minutes.
25 minutes more?
Yeah, but some of that surely for questions.
Okay, so I have better stop about now. So you got saved from the code, but I'm sure they'll make the slides available. Otherwise, you can go to YouTube and find more code explained by me than you could possibly want to see. But basically, we need to do resource management. We need to do generic code. I showed you the vector, which manages a resource which is memory, and anything else that's an element. And we need to write code against such things. That's the basic point. And I think maybe go back to there and then take questions.
I wonder if we could have a volunteer to do a mic at the other side of the room, please. Thanks. Right, who wants to kick off? Do you have any starter questions? Yes, we have one over there.
Are there any features you regret putting in C++?
That's a question I hear fairly often, and usually the questioner has some idea, and the answer is basically no. All the major features are necessary to a lot of people. On the other hand, I can't think of a single major feature that I couldn't do better now. That is, you do learn, but because you can't change things, and you can't change things in a way that breaks existing code. You can't actually fix it, and that hurts. Any major feature you take out, you'll hurt a couple of 100,000 developers and what they are developing. That's the low end. And if you take out something minor, it's irrelevant. So I've gone through the major features. They have a place. I've been lucky. There was somebody up there.
Thanks. Yeah, sort of a related question. I was just going to ask you. So you mentioned this conflict between the need, the desire to improve the language, but also to keep backwards compatibility. Do you ever think, it'd be great to just start from scratch and make a new language, taking the best things and with a clean slate?
Yes. It's something that occurs to me very often, and it's something people tell me, you really should stop trying to fix this old crud and do something better. Can't you do something better? And the answer is, yes, I can do something better. It's not actually hard. I have a lot of experience. I have conjectured I could do something that do more things better than C++ in about 10% of the space and feature set that C++ has. There's only one snag. The old stuff doesn't go away. And whenever people have designed a language that's really much better and more beautiful, they find that they can't serve the range of uses that is already there. They simplify, usually simplifying the programming model so that they lose the performance advantage. And furthermore, it takes a lot to build the tools infrastructure and the education infrastructure that goes around a language. And so each time I've felt tempted, because I've got this great idea, and instead of spending 10 years to get the C++ community to accept it, why don't I just build a new one? And the answer is, if I build a new one, I'll have to spend 10 years getting the first sort of 10, 20,000 users. And in between that, in that time, C++ would evolve. And if my idea was really good, they'll have copied it. And my brand new beautiful language would never see any use. And I have essentially always had this idea that I can't design just for myself. If I'm the only user, if it's just for me, why don't I just do Sudoku? It has more chess puzzles. It's this thing, where can I do the most good? And by and large, we have made significant improvements. I mean, the latest thing I've done is improving generic programming with something called concepts, so that we have more precise specifications. I've also figured out how to eliminate memory and resource leaks, and we are now getting that automated so that you can actually run a program that says, no, there's no memory leaks, there's no resource leaks, all the locks have been unlocked, all the file handles have been handed back. We can guarantee that. That was a dream that nobody believed we could do 10, 20 years ago. And in a new language, we could probably have done in a year or two. And if I was a professor, I could get both of my students to use it. It's, if you're dealing with the sort of billion lines of codes and hundreds of thousands of programmers, you can do more. But it takes longer and it's more painful.
Thank you very much indeed for that talk. Very interesting indeed. I actually am responsible as the convener for the functional safety standard, the International Functional Safety Standard on safety software. And up to now, we have, although we haven't prohibited the use of object-orientated, we have actually put in a series of warnings about the use of it and left it to the user. From what you've now said, would you, and in the for what you said in terms of the improvements that have been made in constraining the way memory is used, the abstraction, the inheritance and so on, do you believe the current version of C++ is good enough that we can now remove those sorts of restrictions?
I think it's good enough for the simple reason that it is being used for cars, flight controls, rocket controls. We saw the picture of the Tesla in space. The SpaceX rockets are programmed in C++. They can land when they're finished. That's a very difficult exercise. Yes, it can be done. Now, the question is, how do you do it well? And about 10 years ago, I worked with Lockheed Martin for writing the coding standards for the Joint Strike Fighter. And so the F-35s and actually also the F-15s are programmed in C++ these days. And they don't actually fall out of the sky very often. So first of all, you can do it. Secondly, let's have a look about how we can do it. Because I have been working on that, and if I'd actually got to the end of this, I was going to say that if you use the whole language, by definition, most of the programs you write are wrong. Like, it takes a brain, it takes putting the statements in the right ways, putting the abstractions in place to do something right. And so basically, we need to distinguish between what can be done and what you should do, what's effective. And so we need guides. And what I want to do here, no leaks, no memory corruption, no garbage collector, because a lot of what I'm interested in is real time, like flight controls and brakes, not to mention my coffee machine. I'm just pointing that out because it's not all fancy stuff. If the coffee machine doesn't work right, the coffee tastes disgusting. And no limitation of expressiveness. You can make anything safe, just stop people from doing anything. And I wanted to run as C++, and yes, I want to use ISO C++. It's tool enforced. There's a lot of attempts to get there. There's the safety guidelines coming out of, where is it, Pittsburgh. There's the MISRA, which I think are fairly primitive. The JSF++ for the fighters, they're all used in various places. Just about any car manufacturer is developing their own superset of the official rules. And I want it tool enforced, because you can't just tell people who wants to write, say, 2 million lines of code, more if you include the tests of the code that's being deployed. But a lot of these systems have 1 million or 2 million lines of code deployed. You can't just tell people don't make mistakes. That doesn't work, it doesn't scale. So you need tool enforced. This is being done. It's not deployed at scale in many places, but for instance, the no leaks thing is being used at million-line programs, and it's being shipped with Visual Studio. So if you have Visual Studio, you can go in, ask for the core guidelines, ask for the for the memory corruption checking, and it'll guarantee that you don't have any. Basically, the code runs into 3 categories. The stuff you can prove is safe, the stuff you can demonstrate to be unsafe, and the ones where the analyzer gets confused and you need a human to look at it. That's the current state. It's coming in Clang. Clang Tidy is working in this direction too. This project here, the Core Guidelines project, is a joint project, open source. It's available on the web. There's Microsoft and Morgan Stanley, that's where I work, are probably the main contributors, but also Red Hat and Facebook and some Googlers. This is a fairly ambitious project. This is why the Holy Grail is up there. And the way that is done is that we start with some high-level rules. That's where the core guidelines and the Joint Strike Fighter rules differ from other rules. They tend to work bottom up. I work top down. First explain the set of principles you're trying to work with. This is suitable for humans. This is the overall thing that allows you to remember what rules there has to be. And then you go to the rule enforcement of the individual rules that can be tested, because there's actually about 400 rules, and I think about 350 can be checked to some degree. To some degree is this triple that I just said: safe, unsafe, get a human. And so we work on that. It's not minimal orthogonal, it's not meant to be, but it is eventually meant to give us that. We are then branching out in things that we know, code that we know are error-prone, logic errors that can't be caught easily by humans, and also performance bugs that. So I recommend looking there. That's where I'm working in that domain. And I'm actually working with some of the ISO groups that do deal directly with safety.
Thanks for the amazing talk. My question is regarding the introducing kids to programming. So what are your thoughts on a kid being introduced to programming via high-level languages or low-level languages? Because many times when a kid is introduced to programming languages like C++, they spend most of the time fixing compilation errors rather than solving the problem. So, like, if you introduce a kid to a high-level programming languages to start programming, so it might it might help them learn the language and to solve problems and get into programming easily. So, what are your thoughts on that?
I'm not sure I understood all of it. So, if I answer the wrong question, correct me. What was the question about state?
It's more about like the learning curve of lower level programming languages like C++ is quite steep. So if you want a kid to get into programming, like, would you rather start with him with high level languages like maybe Python, or would you throw C++
no.
at him?
First of all, the distinction between high level and low level is I think, bogus. Depends what you're trying to do. Python is easy to use. Doesn't mean it's high level. If you want to easy to use something that uses the hardware well, you almost always get to C++ or C. It's just underneath it, it's a level. So the AI ML stuff is usually C++, and you see nothing but the Python. If you're using some of the data analysis workbooks, I've forgotten what it's called.
Jupyter Notebook?
What?
Did you mean Jupyter Notebook?
Yes. Look at the bottom. It's all C++.
Yep.
And so if you have professional programmers doing engineering, I don't think they should, by and large, do it in Python. Writing the test scripts, fine. Writing the user interface, fine. Just like you don't actually want the drivers in the car to use anything more but the steering wheel. Don't let them anywhere near the code. And so some language has to work at the low level where it's dangerous. The question is, how do you get off the dangerous and hard to use parts? And that's where C++ comes in. It's really good at using hardware. If you have a 30 core machine and you want to use those 30 cores, the lowest level of whatever you do will be something like that. And then you can put an easier to use level top. And quite often then on top of that, you get another language or another system. But somebody has to be down there. You don't write your JVM or your JavaScript interpreter in JavaScript. you write it in C++, with a high probability, meaning most of them do it that way. So there's a place of C++, and it's not everything.
Thank you for your interesting talk. I have a question regarding a point on your slides, which was the efficient expression of ideas. And my question is that, for example, in prepositional logic, you have a pictorial representation of logic and also the syntactic representation. And the example is, for example, A implies B could be written as, it is not the case that you can have A and not B. So they're two of the same thing. Yet the pictorial representation of this is exactly the same. So my question is, could it be in the future that one goes away from syntax and one essentially programs by manipulating human recognizable patterns? Because, in other words, the syntax could be represented in many ways for the same idea, yet there is only one pattern that represents one idea. So I hope I...
You can represent everything as logic, and you can represent everything as in lambda calculus. The problem is that quite often you can't say that very elegant in those things, and people want other things. They want to choose the loudness on the speaker by twisting a dial, not by expressing the logic that says what the end number is. So a lot of what we are doing is to provide easy-to-use interfaces to something that is engineered with precision. And the precision has to be relative to what we're trying to express. There are parts of C++ where you actually express it in first-order logic. Let me show there. Something that, let's see. No. So I want, no. I want to express that something can be sorted and that something is something you can traverse in a forward manner. So I want a forward sortable range. That is expressed as being a forward range, and the thing you use to access it is sortable. And so some of the really fundamental things in the standard library is actually specified like that. And whichever sort you're using, you will find that the requirements for sorting, and different algorithms have different requirements, are indeed expressed like that. But what the user sees, if the user is a serious software engineer that's actually working on the hardcore, that's what they see. The user sees this, sort a vector. It's something that's sortable and is a random access range. That's defined up in something up there. And if you want to sort a list, it'll decide, well, it's sortable. By the way, sortable means that you can move things around. You have random access, and the elements have a less than operator. So that's defined in that exactly precise what you're doing, but the user sees this level of thing. And by the way, the distinctions between a random access sortable sequence and a forward sortable sequence can be recognized by the machine so it picks the right algorithm. And so we're doing it down near the bottom. And people are doing things, again, way up high, where they twiddle a knob and they get what they want, and it goes down through. You could have a knob or you can have a slider. They turn out to be the same thing underneath. They just pick a point on the scale. So it's happening. But not all over the place because it's a general purpose programming language and it's really hard to deal with hardware and the wide range of people's needs.
Thank you very much for a really interesting talk. I was particularly interested in the fact that you started your career looking at distributed systems. And this is an issue that sort of plagues many of us still today, how to program successfully over distributed systems, how to do concurrency well. And for years we've had abstractions to manage this, like threads, mutexes, that sort of thing. And they've been in C++ and other languages for sort of 20 years or so. And we've done it very badly with that level of abstraction. And I wondered if you could say something about the abstractions that you think may bring us into a world where we can really successfully program concurrent systems and work with distributed hardware.
Wonderful question. My PhDs were partly on that. And I left Cambridge thinking I knew about 25 different wrong ways of doing concurrency, meaning that they could be right for something, but for a very small minority of use cases. And today I think I know at least 45 bad ways. I think the thread and lock model that we're using all over the place at the systems level is about the worst way of writing code. It's really hard to optimize, and it's really easy to make synchronization errors, data races. On the other hand, we have to deal with it because of, this is not just C++, so we're talking about a trillion lines of code or more. And a lot of them directly or indirectly interact with that level. So for C++ 11, we for the first time managed to lift this away from the machine into something that was type safe. And so the standard library provides the notion of a thread. It provides the notion of a task running on a thread. It has condition variables. It has different kind of mutexes. It has locking mechanisms that allows you to avoid deadlocks, simple deadlocks, and things like that. So whatever else we were doing, we had to get that stuff a bit under control because it was chaos before. Void stars and macros for those of you who have done POSIX. That done, we're nowhere near it. I think the only really good way of thinking about these things do not involve synchronization at the user level. That is, I'm for just about anything that involves sort of message passing and no shared state in a concurrent system. There's a couple of answers to that. Futures, message queues, things like that. We're working on it, but that's the next level up. And I know there's higher levels, but now you start getting to be specialized. People talk about concurrency and parallelism as if it was one thing, and as it's not. Parallelism and concurrency are two different things. One depends on the other, but they're different. And there's variations of how you want to express it that depends on what you're doing. The hardware control guys are not thinking in the same way about concurrency as database guys, and they're not thinking at this, etc. And I lost a thread. Sorry. There's a lot of stuff being done in the context of, interestingly enough, games and real-time controls. That's being done. We'll see something that over the years. But if you can get rid of the shared state, you get rid of most of the problems.
Great. Well, this has been an absolutely splendid talk. I've no doubt the questions could go on, but this is the time where we have to go informal and leave further interaction to social events and dinner and so on tonight, because at 4 o'clock We've got a happy 40th birthday event for Cambridge University Radio, and those people who want to participate in that, which is actually across the road in Storey's Way at Fitzwilliam College, should gather at the Portals Lodge at 4 o'clock. So it's a good job that we're coming to a natural break in things at 5 to 4, which gives people a chance to amble over there if you're interested. And now, of course, I'd like to propose a vote of thanks to Bjarne, who's given us a great talk, and thanks for this, Bjarne.
Thank you. Thank you.